Hello and welcome to the webinar, Driving Stagewise Implementation with Jameson Cell, IsaMill and Albion Process. This isn't just an overview of the three technologies. It's a powerful concept for self-funding the improvement of your concentrate. First though, some quick housekeeping. You'll find you are muted. This is simply to keep things quiet for the webinar. Ignore the raise hand button. Instead, just use the Q&A button for any questions that you might have. And on that, you can ask your questions at any time during the webinar. And at the end, while the webinar is closed, we'll still actually be on air for a few minutes taking your questions. So I'll introduce you to our presenters. For Jameson Cell, we have Jessica van Sliedrecht. For IsaMill, we have Kai Johnston. And for Albion Process, we have Sarah Dowling. But we'll also start and finish with Sarah to take us through this great concept and to give us some examples. So let's start with Sarah Dowling. Our hydro team evolved this concept with the minerals processing team to help enable you and other clients to access improvements more easily. Let's take a look.
Thank you, Steve. So let's look at the motivation for the stage-wise implementation approach. As a gold mine deepens or expands, the site will need to deal with refractory sulphide ore. A stage-wise approach to implementing technologies capable of treating such an ore has the following advantages. It provides an entrance strategy for projects which are unable to commit to upfront lump sum capital investment. It allows for revenue generation whilst the subsequent stages are completed, and it staggers expenditure over time to improve cash flows. Ultimately, it allows sites to process all of their ore on-site and achieve high overall gold recovery to doré. So let's look at this from a flowsheet point of view. We start off with the baseline flowsheet of the ore being milled and sent straight to a cyanide leach plant. In stage 1, we implement a Jameson cell or Jameson concentrator and produce a concentrate which we can sell. In stage 2, we implement an IsaMill. The IsaMill takes the flotation concentrate, grinds it finely, and this is then fed into the existing CIL circuit. In this way, all of the ore is treated on site and all of the gold is recovered on site. In stage 3, we look at the full implementation of the Albion process. The IsaMill product is sent to oxyleach reactors, where the sulphide is converted to sulfates. This oxidized residue is then sent to the CIL plant and gold is recovered. So what is happening behind the scenes? Well, in our baseline flow sheet, we have our oxidized ore, which is going to the CIL plant. Here, cyanide is leaching the gold from the ore, and the gold is recovered on the carbon and sent to the gold room and recovered as doré. In stage 2, we implement the Jameson cell, and here we have a mixture of the sulphide and the oxide ore, where the oxide ore reports to the tailings and the concentrate reports to as a saleable product. In stage 2, where we implement the IsaMill, we see the sulphide being finely ground and then sent to the CIL circuit. The finely ground product allows the cyanide to attack and leach the gold from that sulphide ore, and then it is recovered on the carbon and into gold in the gold room. Finally, behind the scenes of the Albion process, we have not only the ultrafine grinding, but we also have the oxyleach reactors leaching the sulphide to sulfate. This makes the gold hosted in the sulphide accessible to the cyanide, and it is able to leach the gold and be recovered.
Thanks, Sarah. It's a powerful and enabling concept. So let's take a look at what can be the first technology in that stage-wise implementation, Jameson Cell. Here is Jessica van Sliedrecht.
Thank you, Stephen, for the introduction. So when looking at recovering value from the sulphide material present in these deposits, selective flotation is one of the most common methods for concentrating and recovering sulphides. The sulphide minerals have different characteristics to the oxide material, and through the use of specific chemicals, we can target those valuable sulphide minerals and render them hydrophobic for flotation. This allows effective separation from the oxide and other gangue which can proceed to CIL. And depending on the concentrate quality from flotation, the concentrate can either be sold to smelters as outlined in the Stage 1 implementation, or if requiring any further treatment, this could look like the Stage 3 implementation with the Albion process. So Jameson cells have been effective and beneficial in gold flotation. Looking at Jameson Cell technology as a whole, there are now over 500 installations globally in a range of commodities and duties. There's over 35 years of experience in operations and design since the first development and installation at Mount Isa in the late 1980s. And since then, the Jameson Cell has undergone a number of design improvements to enhance the operability, maintainability, and performance. And we're now up to what we call the Mark V design. So one of the key components of and design aspects of the Jameson Cell is the fine bubble size that it produces. So this is around 500 micron in size, and that's found to greatly increase the flotation rate kinetics of particles, which is highly effective for fine and coarse particle flotation. The cells are able to stabilize fast to any changes upstream, and that's greatly driven by one of the design improvements, which was the tails recycle mechanism, which I'll touch on in a moment. The cells also have a large carrying capacity per unit. They're self-aspirating, so they can generate bubbles through inducing a vacuum and air from the atmosphere, and don't require any blowers for production of bubbles. They're highly flexible in their duty and can operate from a high grade to a high recovery. The wash water system of the Jameson Cell enables the froth to be washed and displace the water carried over in the froth phase, reducing the entrainment and allowing high upgrading stages. So the tails recycle mechanism that I just mentioned before, so this was a key design improvement of the Jameson Cell and enables a constant downcomer flow, irrespective of any upstream changes. So the downcomer flow will consist of the fresh feed made up with the difference with tails recycle. Looking at the Jameson Cell principles of operation in the downcomer, pressurized slurry enters the downcomer through a nozzle at a high jet velocity. So that jet entrains air in the headspace, which creates a vacuum inside the downcomer and draws slurry up the downcomer. So as you can see in the diagram there, the jet plunges into the slurry surface, and that causes entrained air to shear into the fine bubbles. This is a highly effective mechanism and enables the cell to not require any external blower for air supply. That high intensity mixing zone leads to high probability of bubble particle collision and contact, and only a few seconds resident time is needed in each downcomer. So the Jameson cells can operate with a grade or recovery focus, allowing them to work across all flotation duties in roughers, scavengers, and cleaners. So looking at what a Jameson concentrator design looks like, we have an example on the right here, which would be a standard design for a copper concentrator. So this is fundamentally the same as a traditional concentrator design. However, you can see it's greatly simplified and reduced the number of flotation cells required. When designing a Jameson concentrator, the Jameson cells either operate in high grade or recovery duty, and translating that to this flow sheet. In the rougher circuit, we can see that the first cell is operating as a rougher scalper. So if liberation permits, a final concentrate can be obtained from the first cell, and that greatly reduces any downstream cleaning requirements. The second cell in the rougher circuit, the scavenger, focuses on recovering the remainder of the material in that stream. Now looking at the cleaner circuit, so we have a cleaner scalper that's able to produce a final concentrate grade from the freshly liberated material from regrind and send that to final concentrate. The cleaner scavenger then takes the remainder of the material and recovers this with the upgrade to final concentrate grade in the recleaner cell. So here's a typical flow sheet for gold, and you'll notice it's a lot more simple than the concentrator shown just before. And gold circuits are typically a lot less complex than other commodities. So with high stage upgrading ability, only 2 Jameson cells in a rougher scavenger configuration are usually required to reach final concentrate grade targets in gold. So with this flow sheet design as well, you're able to operate it in a flexible manner along the grade recovery curve, depending on the focus, whether it be on concentrate grade or recovery. So for the stage 1 implementation with a focus on concentrate grade to smelters, this flow sheet would allow you to operate at a higher grade, lower recovery, and then when undergoing further treatment in stages 2 and 3, you could operate this a bit more aggressively with a focus on recovery. So here's a second flow sheet, which is a variation of the first one. This one includes the addition of a third Jameson cell in a cleaner duty. Usually include this one if the scavenger concentrate requires some further upgrading to reach that final concentrate grade. So this flow sheet configuration is mainly suited to the stage 1 implementation, where concentrate quality is important for on-sale to smelters. So now that we've gone through some flow sheets, we'll now take a look at some Jameson cells operating in these duties. So the first one here is a rougher scalper at Newmont Cadia. And what you can see on the graph there is the Jameson cell pilot testing results that were completed on site on the rougher feed. And also in the graph is the mechanical cell bank performance. What you can see is that the Jameson cell can upgrade considerably better than the operating tank cells. And that meant that installing that cell at the head of the mechanical bank as a rougher scalper allowed them to produce the bulk of the final concentrate and gold recovery in the first cell and greatly reduce downstream cleaning requirements. So overall, the gold was able to be upgraded from 0.7 grams per tonne to 50 grams per tonne. So the second example we have here is another Jameson cell in a rougher scalper at a North American gold site. So what you can see on the graph is the operating performance of the cell across a range of ore types. And this installation allows operation to achieve a high gold recovery of 91% at a final concentrate grade target, at final concentrate grade of 47 grams per tonne. This is considerably higher than what the design was initially set at 70% recovery and 40 grams per tonne. So that means that they're able to produce the bulk of the final con from the Jameson cell and considerably reduce downstream processing requirements. So with all the flow sheets and results we've taken a look at, the Jameson cell can add significant value to circuits, and those benefits can really be amplified utilising the Jameson cell and IsaMill technologies together and what we call the Jameson concentrator. So with Jameson concentrator, we normally see significant reduction in footprint, CAPEX, OPEX, as well as improved metallurgical performance. To summarise what we've gone through today, the Jameson cell is a well-proven, high-performing, mature technology. It's highly effective and beneficial in gold flotation. It can add value through all phases of the staged implementation. And through the inclusion of the Jameson cell and Jameson concentrator in the flow sheets, you'll be able to see significant reductions in footprint, power, CAPEX and OPEX.
Thanks, Jess. Jameson Cell can yield for you some very fast returns, so let's take a look at what might come next, the liberation of more using IsaMill. Here is Kai Johnston.
Thank you, Stephen. Today I'm going to be talking about the IsaMill and how it can be used to unlock the value inside your project. So before we can establish what actually happens inside the IsaMill, I'd like to talk about how the IsaMill has come to be. So as you are well aware, fine grind mineralogy requires a finer grind to unlock and liberate the surfaces to provide selective environments for downstream flotation, and that grinding finer requires an exponential increase in energy to meet that grind size. In the 1980s, Mount Isa was experiencing finer grained mineralogy, which meant that they required a 7 micron grind to essentially maintain downstream cleaner performance. Conventional mining technologies that were available at the time were tested. However, they ran into 3 key issues which limited the implementation of the 7 micron grind. The first one was that the power consumption that was required was way too high, and it essentially made the project uneconomical from both a CAPEX and OPEX perspective. The ball and tower mills that were available at the time were ineffective below 20 to 30 microns. And finally, the last reason was that the steel internals and steel media that was used in these mills had a negative effect on downstream flotation performance due to the galvanic interactions that they produced. So this led to the engineers on site looking outwards from the industry to help find a solution to help them treat the fine-grained and complex ore bodies. And this spearheaded the development of the IsaMill. So what is an IsaMill? Well, the IsaMill is the world's only horizontal high-intensity stirred grinding mill, and it is a mature technology with over 150 installations spanning across a 25-year operating window. It has installations in copper, gold, lead, zinc, molybdenum, PGMs and other commodities such as magnetite and rare earths, providing a wide range of applications. And with the technology maturity, there's been many years of lessons learnt to provide GT with best practice for design and operation of regrind circuits. Inside the IsaMill, ceramic media has been introduced to essentially minimise the galvanic interactions that occur inside the mill, replacing the steel media that traditionally had, and steel internals traditionally had, a lot more galvanic interactions. The IsaMill also introduced a high intensity mixing mechanism which provided, greater high energy intensity and more abrasive environments, which assisted with providing more energy efficiency for the grinding and collisions. The IsaMill also introduced ceramic media in greater volumes and at finer particle sizes to ensure that with the greater surface area there was more particle media collisions to provide that abrasive attrition grinding environment. The IsaMill also introduced its own internal classification mechanism, and this reduced the complexity of the IsaMill regrind circuit as closed circuit cyclones were no longer required to meet the target product size. Now, what is actually happening inside the mill? Well, both media and slurry enter through the feed end of the mill where it comes into contact with a series of rubber-lined discs. Each of these discs have kidney holes mounted close to the shaft, and they rotate at high tip speeds of around 20 meters per second. This rotation provides media and slurry with extreme amounts of agitation and centrifugation, forcing them to the outside of the mill close to the shell. And this is essentially where most of the abrasive environments are occurring and most of the particle slurry collisions are going to be. The finer particles, they stay closer to the shaft of the mill where they are allowed to pass through the kidney holes and exit out to the discharge of the mill. What you'll notice is the spacing between each of the discs is a lot smaller in the last disc when you look at the relative position of the last disc to the rotor product separator. This smaller spacing is deliberate to allow for more centrifugation to the outside of the mill, which pushes all the media and slurry in the area out to the shell of the mill. On the discharge end, in yellow on this picture, is the rotor product separator, and this acts like a pump impeller to force all that media and all those solids that have been pushed to the outside back to the feed end of the mill, which is where all the grinding occurs and back to get ground down even further. This product separator mechanism is what not only retains media inside the mill, enabling the mill to have a horizontal design, but it also provides the mill with a sharper cut size as coarse materials cannot short circuit the mill. And this sharper cut size is very beneficial for flotation and downstream processes like leaching. So the advantages of the IsaMill. So the first advantage of the IsaMill is it provides an inert grinding environment through the replacement of steel internals with rubber-lined components and steel media being replaced with ceramic media. It also features a horizontal design, which is low in height when compared to the superimposed vertical regrinding mill on the model shown on the slides. And this is important as it reduces the steel and concrete required for reinforcing the structure in the air. The energy efficiency and energy efficient transfer mechanisms of media to slurry allow the mill to have a compact design, and as there are no external moving parts on this mill, there is added safety for maintenance and operators working in and around the mill. Since maintenance occurs on the floor and due to the horizontal configuration allowing work to be done lower to the ground, there is an ease of maintenance as no one requires to harness up to get into the mill and inspect internal components or work on inevitable wearing parts. So now we've seen how easy it is to implement an IsaMill in your operation. I want to talk about how easy it is to scale up the mill. IsaMill scale up occurs through the signature plot procedure, which is used to obtain the specific energy requirement for your specific ore and your specific duty. The specific energy requirement is different to a bond work index test as it doesn't use a correction factor or correlation to give you the specific energy result. Instead, it takes a direct power readout with the direct tonnage going through the mill. The signature plot can be done in any IsaMill from the M4 up to the M10,000, and the test work conditions are tailored to your application to ensure that you get the best result for your ore body and to ensure that you get the one-to-one scale up from lab scale to full scale. Test work is also completed by an accredited lab which undergoes GT's QA/QC procedures to ensure that you get the best result every time the signature plot is completed and to ensure that the one-to-one scale-up condition is met. As I said before, the IsaMill has its own internal classification mechanism which not only simplifies the circuit allowing for open circuit operation, but it also achieves the sharpest cut size out of any other regrind technology in the world. This plot compares the difference between performance of the IsaMills at MRM to the SMDs at Century, and in this case both P80s for both technologies were quite similar. However, when you look at the results a little bit more, you notice that the IsaMill achieved a sharper cut size with a finer P98 of 19.5 microns versus Century's 38 micron top size. Now, the sharper cut size is quite beneficial for flotation downstream. However, most of the value in achieving a sharper cut size can be seen in a leaching circuit. In this example, we can see the effect of the cut size on the leach extraction in a copper concentrate leaching circuit. 4 milling technologies were compared and each one achieved a very similar P80. However, just like in the previous example, the P98 of the IsaMill was the finest and so was the sharpness of the cut size. Transferring this over to the performance on the downstream leaching, we can see that the IsaMill with the sharpest cut size and the sharpest size distribution achieved the best leaching extraction as it essentially minimised the losses to recovery and performance from passivation. So, although you can see that the P80s are similar, the leach extraction objective is not quite the same, and the IsaMill compared to the MetProtect mill achieved a 4% greater recovery. Quantitating the effect of this P98 to P80 on revenue in a 145,000 tonne per annum copper plant, this shows that the revenue losses can equate, due to the loss in recovery from passivation, can equate to a $6 to $11 million a year revenue difference. I would now like to introduce the KCGM roaster replacement project, which is an example of a stage 2 implementation in a gold circuit using an IsaMill. In this scenario, the imposed SO2 limits were reduced by 80% down to 400 micrograms per cubic metre from the original limits of 2,000 micrograms per cubic metre in 2013. This had an impact on their roasting capacity, and it meant that the site had to drop the capacity in their roasters by 30% to meet this target. Furthermore, this site was also experiencing a change in their sulphur grades, which meant that they needed increased production to meet their operating demands. After extensive technology reviews between looking at things like the ultrafine grinding and other oxidative leaching technologies, it was determined that from an NPV perspective, ultrafine grinding directly into CIL provided the most benefit for this site and was able to meet the emission reduction targets that the site needed to remain operational. The M3000 IsaMill was selected to target a size reduction of 120 micron down to 10 micron, and this provided enough of a size reduction to maintain the operating targets for the site. After the successful implementation of this M3000, a few years later, the M10000 IsaMill was also installed in 2015. This allowed for the immediate shutdown of these two roasters and eliminated the SO2 emissions on site overnight. Plant production rates were also able to be maintained, and the finer P80 target of 10 to 12 microns essentially resulted in a gold recovery increase from 75% to 92%. In summary, the IsaMill provides the sharpest product size distribution out of all other grinding technologies due to its own internal classifying mechanism. The horizontal design of the mill ensures ease of maintenance and greater safety for anyone working in and around the mill. And as we've demonstrated, leaching is impacted by the sharpness of the size distribution. And the IsaMill ensures that losses to passivation are minimised due to ensuring that you get a sharp size distribution. If NPV allows, the IsaMill can also be used for a stage 2 implementation or furthermore in a stage 3 implementation. Thank you.
Thanks, Kai. IsaMill is incredibly flexible. It'll clearly process fine or coarse feeds and liberate more for you. So let's take a look now at what may come third in your stage-wise implementation, a superior treatment of sulphide feeds using Albion Process. Here is Sarah Dowling.
Thanks, Stephen. So what is the need for the Albion process? As we discussed earlier, as you move from oxide to sulphide ore, you'll get a mixture coming into your plant. The sulphide ore cannot be treated in your CIL plant and would report to the tailings, resulting in a lowered gold recovery. So we need to do something about it. There are 4 commercialized pre-treatment processes for refractory gold ore. The first is roasting. This is a high temperature process. SO2 is generated. It is suited to low arsenic, high pyrite ores, and it's also suitable for high organic carbon ores. There's biological oxidation, or BIOX. This makes use of bacteria which can do the oxidation for you. It is a low temperature hydrometallurgical process, and it is suitable for stable feeds. Then there is pressure oxidation. As the name implies, it's a high temperature, high pressure process. It does have a short residence time, but the equipment is specialized and the operational requirements are also specialized. Finally, there is the Albion process. The Albion process makes use of ultrafine grinding and atmospheric leaching to convert the sulfides to sulfate. It is suitable for variable feeds and variable throughputs. Let's look at this some more. So what are the advantages? Firstly, as Kai mentioned, the IsaMill generates an ultrafine ground product that does not passivate in the leach. The oxy-leach reactors are specifically designed for sulphide leaching. They feature specialized baffles and nozzles, standardized sizes, different types of materials which are suitable to your project, and these include mild steel, LDX 2101, 904L, and SAF 2507. The hypersparge is used to deliver oxygen at very high utilizations of up to 80%, and this would help with your OPEX. If we jump into the fundamentals, what is at the heart of the Albion process? It is the mass transfer of oxygen from the gaseous phase to the liquid phase. There, the ferrous in your liquor is converted to ferric, and this affects the oxidation of your sulphide. The rate-limiting step of this whole process is the mass transfer of oxygen from gas to liquid. And if we look at our oxygen transfer rate equation, we can see what we can play around with to try and make this as fast as possible. So, the oxygen transfer rate when using the hypersparge is 2 to 5 times higher than with an open pipe sparger. And this is because the hypersparge delivers a high shear jet into the slurry, and this creates microbubbles which peel off from the jet. This increases your interfacial area and increases the oxygen transfer rate. If we look at the design of the hypersparge, it really is all about operability. There is a ductable valve which allows for live removal. Slurry ingress into the gas lines is prevented by the 15-degree inclination on the mounting of the tank nozzle, as well as the check valve. The ceramic nozzles used in the hypersparge are protected by a SAF 2507 housing, and the nozzles can last for up to 10 years. So if the Albion process is sounding like a good idea for your project, let's take a look at what the implementation path is. We start off with a concept or amenability test in phase 1. This is a pass-fail test where the conditions are such that you give it the best chance to pass. If, however, this test does not pass, we can hand on the heart say it's not worth going further. In the pre-feasibility stage, or stage 2, we look at the processes which would influence your OPEX and CAPEX. We take a look at grind sensitivity. So, can we grind less fine? At what point do we need to grind to get the desired result? We also do an IsaMill signature plot at this point so that we know the specific energy input for your project. In phase 3, or in the feasibility stage, we look at grind sensitivity again. We look at the signature plot again, and this is because the sample that might have been generated by site could have changed. If the sample has not changed with geological exploration, this would not have to be repeated. We also look at SOx variability. This essentially is the degree of sulphide oxidation which you need to achieve the highest gold recovery. And we look at density sensitivity, and we look at how far can we increase the density of the pulp so that we can minimize your reactor volume. Finally, there is a bulk leach done to generate sample for settling and flotation test work, and also slurry rheology. In this phase, all the design parameters generated by the test work would feed into a Class 3 engineering study. It is important to note that for the Albion process, we actually do not require a pilot plant to be run. From this lab bench scale test work, we can do the full design, and we can provide a process guarantee. The bankable feasibility, or phase 4, is the final stage, and this is very project dependent. It would look at advanced variability test work, and the scope of work would be determined based on the completion of the Class 3 engineering study. GT works closely with accredited labs so that we know the quality of the work can be trusted. We provide regular updates throughout the test work programs with you, the client.
Thanks, Sarah. Albion process can work well in difficult and varying feeds where other technologies may not. So now let's explore some case studies in a stage-wise implementation of all three. Back to Sarah.
Thanks, Steve. Okay, so in this case study, we look at 4 different projects. I'll just run you through the graph. So the blue bar is the gold recovery if no pretreatment was required. This would be if you were to send your sulphide con straight to the CIL circuit. In project 2 and 4, you can see that the gold recovery is very, very low, and this is because the cyanide cannot leach the gold from the sulphide matrix. The orange bar is the application of phase 2 or the ultrafine grinding in an IsaMill. In projects 2 and 4, there is not a significant uplift in gold recovery. And so for these projects, you would consider the current implementation of stage 2 and stage 3. The grey bar looks at the full implementation of the Albion process and gives the uplift and gives the total gold recovery when the Albion process is applied. For projects 1, 2, and 4, the increase in gold recovery is 30, 60, and 60% respectively. Let's take a look at the economics of a particular project. We consider a project where the underlying sulphide deposit consists of pyrite-hosted gold with significant non-sulphide gangue, such as silicates and carbonates. The float circuit required to treat this con is one rougher and one scavenger. The saleable concentrate produced by the rougher and scavenger achieved gold recoveries of 85% at a mass pull of 6%. The con produced was 36 gram per tonne at a 75% payable contained metal value. This will bring additional revenue forward whilst the remaining design, installation and commissioning is completed for stage 2 and 3. In stage 2, the IsaMill selected was an M7500. In this particular project, it is important to note that stage 2 and stage 3 were implemented concurrently, as the gold recovery with just an IsaMill was only 39%. So this IsaMill allowed for a P80 of 12 microns to be produced. The implementation of the full Albion process saw the installation of 7 OLR 400 oxyleach reactors with a residence time of 48 hours. After the Albion process was installed, 96% of the gold recoverable via cyanide leaching was achieved. This equated to an uplift in gold recovery of 76%. The CAPEX distribution across these three technologies was 25, 28, and 47%, and the OPEX distribution was 12%, 35, and 53%. With an assumed gold price of $65 per gram, the revenue generated under stage 1 with the implementation of the Jameson cells generated enough revenue to cover the initial capital outlays of the later phases. So, in conclusion, a stage-wise approach to implementing technologies capable of treating refractory ore can extend the life of the operation, and it provides an entrance strategy for projects which are unable to commit to upfront lump sum capital investments. It allows for expedition to revenue, while staggering expenditure. It improves cash flow and allows completion of the subsequent stages to achieve high on-site gold recoveries and a robust process for future gold production.
Thanks, Sarah. Stage-wise implementation can really enable improvements where you may not have thought they could be viable. Now, that's the end of the presentations, but it's not the end of your chance to get value from our panel. Our team will stay online, ready to answer your questions. So I want to thank Sarah, Jessica, and Kai. The guidance they provide you is valuable. And I want to thank you for joining us. So stay online, please, to ask more questions, and look out for the email in a couple of days that will contain the presentations you've just seen. Thank you.